Well, good morning, everyone. It's a couple minutes after 10 a.m. We have quite a few people who have joined the webinar, and there are a few more joining as I'm speaking. But I think in the interest of time, we'll get going. And over the next few minutes, I know there will be plenty of other folks joining us. First of all, welcome to the Hortonworks and Zementis webinar on Hadoop's advantages for machine learning and predictive analytics. My name is Mark Rabkin. I'm the Director of Business Development for Zementis, and we are very appreciative that you've chosen to spend the next hour or so with us today. You will hear a bit more about Zementis during the webinar from our CEO and founder, Michael Zeller. But before we get started, I'd like to cover the typical housekeeping items that get covered at the beginning of a webinar. At this time, we've muted all of the attendees due to the number of people that are in attendance. However, there will be times for questions and answers at the end of the call, and you should see a question dialog box where you can type in your question, and I will be monitoring that, collecting the questions. And don't wait till the end of the webinar. If something occurs to you, please bring that in, and I will sort through the questions and ensure that as many of them as possible get answered. In addition, I did want to mention that all of you who are in attendance are going to receive an email from us a couple hours after the GoTo meeting. I suggest you take a look at that because it's going to contain a link that will enable you to download a white paper on R and Hadoop that was written by James Taylor, a pretty well-known big data analyst. So there's a lot of good information in that white paper. So keep an eye out for that. The session is being recorded and will be archived, and you will receive an automatic email notification when it's available. You can also, both Hortonworks and Zementis will be posting it on their respective sites. So once again, today's presentation is Hadoop's advantages for machine learning and predictive analytics. We're joined by both Michael Zeller, the founder and CEO of Zementis, and Ofer Mendelovich, who's the Director of Data Science at Hortonworks. Michael Zeller is the CEO and co-founder of Zementis. His vision is to help companies deepen and accelerate insights from big data through the power of predictive analytics. He also serves on the board of directors of Software San Diego and is secretary and treasurer on the executive committee of ACM SIG KDD, which is the premier international organization for data mining researchers and practitioners from academia, industry, and government. If you're not familiar with KDD and you're interested in big data, it's a great organization. We encourage you to take a look at it. Ofer Mendelovich is the Director of Data Science at Hortonworks, where he's responsible for professional services involving data science with Hadoop, including use cases like recommender systems, prediction, classification, and search. Prior to joining Hortonworks, Ofer has held a number of positions from entrepreneur in residence at Xseed Capital, VP of Engineering at Nora One, and Director of Engineering at Yahoo, where he led multiple engineering and data science teams. Ofer and Mike, we look forward to the presentation today. And with that, over to you.
Oh, hi, everyone. This is Ofer. I'm glad to be here today, and thanks for joining us. I wanted to give a quick overview just about Hortonworks. We're a company here in the Bay Area. And really, what our mission is and our commitment to our customers is to drive Hadoop in a completely open source standard, leading the innovation in open source. And everything we do is exclusively an Apache open source, community-driven process. We also care a lot about enterprise rigor. We engineer, test, and certify Apache Hadoop for our customers, so that are with the enterprise in mind, so it's all robust and works really well. And we're also very, very strong collaborative environment with our ecosystems. So we have deep integration with a lot of different companies, including Microsoft, Teradata, SAP, PHP, a lot of other companies, and we really think that the ecosystem is a strong part of our business model.
Thank you, Ofer. This is Mike Zeller, and we're probably one of these endorsements for the ecosystem, so we're very glad, and it's our pleasure to be a partner with Hortonworks here and presenting today. Zementis focuses on the operational deployment of predictive analytics, and that is in the context of big data and predictive and big and real-time scoring. Of course, today we'll have a focus on Hadoop as the ecosystem. Gartner has named us a cool vendor in data science in 2014, and we were recognized by CIO Review magazine in 2013 as one of the 20 most promising big data companies. Our really central vision is to make available a vendor-neutral architecture for data mining and the deployment of predictive tools. That's really central to our idea and our philosophy, and it works really well with the Hadoop ecosystem, and of course Hortonworks as our partner, as you noticed, very open to the ecosystem here. Central to our mission is, of course, the PMML standard, the industry standard. Predictive Model Markup Language is the full name of that, and we'll get into more details as we go along. It's a very central standard for the deployment and the operational use cases in predictive analytics. And at the end of the day, really, it's all about business value, generating better and faster insights, rapidly deploying those models, and executing those models on top of Hadoop. And with that, Ofer, the stage is yours, and back to you. Jackie, can you please hand over the controls?
Okay, great. Thank you. Thanks, Michael. So I wanted to start by talking a little bit about how Hadoop plays into the kind of the new era of big data, and then we're going to talk about some of the advantages it has for predictive modeling more specifically. But the starting point really is that today, a lot of organizations have a data architecture. It includes a lot of different systems, database management systems, enterprise data warehouses, a lot of data sources, a lot of applications on top of this. And part of what's going on in the last year or two, maybe more, is that there's a lot of new types of data. There's server logs, sentiment analysis from the web, geolocation data, things like sensor and machine data coming from cars and devices everywhere. And so there's this kind of a pressure on this architecture to store a lot more of this data, and which is a problem. So we have a lot more data, we have a lot more data types, we have structured and unstructured data and semi-structured data, and the huge amount of data is causing, you know, these architectures to be kind of looked at more broadly. And where Hadoop is kind of emerging as a big component, as you can see in this slide, of what we call the modern data architecture, and in some sense people call it the data lake. The data lake is the idea that you put Hadoop, it's a platform, it's a whole stack that includes a lot of components, but at the basis of it, it allows you to put all of your data stored in one place with, you know, fault tolerance and all this stuff that comes with that, and perform a lot of analytics on top of this data. There's a lot of people kind of move into this architecture that you see here, where all the existing applications coexist with it, but Hadoop becomes a central piece that's used more and more to deliver deeper insights across all these different data sets and all these different data types. And part of the magic that happens with Hadoop, a lot of people adopting it are seeing day in, day out, is that it moves from a kind of I would say, more structured or linear process to a more iterative process, which allows organizations to get more insight quicker. And what I mean by that is, in the kind of the more structured database world, we have a database, we have, and the process of determining or providing analytics is very structured. You have steps in the process, and you have to follow them one after the other. And whereas with Hadoop, we have this thing called schema on read. So the schema of the data is applied to the data when you read it and when you use it for analytics. You don't have to change the schema up front. And that although it may sound a little bit strange to some people who are used to the SQL world for many years, it actually has a lot of benefit in terms of agility and ability to add new data very quickly and use access patterns that are new and interesting, and eventually result in just more agile processes and faster accelerated innovation in organizations. So let me give you one example of that. Actually, I'll give the example after this slide. I wanted to first talk about kind of the tasks that we have in machine learning. So we're going to talk about predictive analytics, but I wanted to give a higher level view on the different, and this covers probably 80 or 90% of different types of things we do in machine learning. So on the left side, you see what I call discovery. So discovery is where you essentially have data and you're trying to understand or detect different patterns in it. And the types of techniques that we typically talk about here is clustering. Clustering, things like k-means clustering or density-based clustering and things like the hierarchical clustering. And the goal there is really to look at data. Data points could be people or could be objects of different types you're interested in, and detect natural groupings in this cluster, in this point. I'm sorry. So that's what clustering is. Outlier detection is where it's kind of a cousin of clustering. So you're interested in understanding what the clusters are, but you also in outlier detection you're actually interested in the points that are not very central to the cluster, that are outlier to that cluster, don't belong to any cluster very specifically. So that's usable a lot in things like fraud detection. You can imagine credit card fraud detection, for example. What we call association rule mining is another version. Again, here we're interested in transactions, and we're trying to find co-occurrence patterns in those transactions. So imagine a supermarket. That's the typical use case is called market basket analysis, where you have a supermarket and look at transactions. You want to find products that are bought together, like ice cream and ice cream scooper maybe, or ice cream and cones or something like this. And then supermarkets use this to kind of place items together to drive incremental sales. On the prediction side, I want to talk about three different techniques here. One is called classification. So when you build a classifier, you essentially take data points that are labeled, and you learn a model how to classify other data points that are not labeled and give them that label. The label is a category. It could be a binary 0 or 1. It could be one of many categories. And you're trying to essentially take a new data point and using this model you learned, predict what category it should belong to. Regression is very similar, but instead of predicting a category, you're trying to predict the value. So it's a continuous value. For example, you want to predict lifetime value of a customer. It's a dollar amount. It's a number. It's not a category. Recommendation is what we think of when we think of Netflix, right? So they have recommended movies, or Amazon implements this, right? And a lot of other companies implement this. Essentially, there, what you want to do is you want to look at items that you bought or movies that you've seen, and look at other people who have also seen different movies and figure out which movies you might be interested from this data. So this is kind of a big map of different tasks. And typically when we do machine learning or what is called data science today, the process is very iterative. First, we kind of acquire the data. Maybe it's on a database, and so if we work with Hadoop, we usually kind of use different tools to bring it over to Hadoop to make it easy to access. But a lot of times we still have to call someone in an organization, sometimes even ask for some favors, and get the data into where we can access it easily and run some of the analysis. Then a lot of the time in data science actually resides in the second box, which is clean the data. A lot of data tends to be very, very dirty, for lack of a better word. It's, you can imagine things like text fields that are just, people write different things in different ways. There's missing data. There's typos in the data. There's negative instead of positive values. There's a lot of different ways data could be not represented well, and especially when you take a lot of data sources and you put them together, there's inconsistencies between that. And so a lot of work gets done in this cleaning phase of the data. Then you visualize and explore the data, and you try to figure out which features might be interesting for your model and how you do feature engineering. Then you create a hypothesis, you build a model based on those features, you train the model, you evaluate whether it's good or not. And typically, in that phase, you kind of do the circle again. A lot of times in data science, you don't get it right the first time, so you have to kind of iterate over and over again until you get it right. Once you get it right, then you can deploy the model to production, and then you do this phase called scoring, which we'll talk about more when we talk about PMML and that phase later on. But then you want to deploy and monitor this to implement it in production. So that's generally how the iterative flow works. And now I want to talk a little bit about kind of 4 points that I want to kind of highlight for you, everybody who's joining here. Why Apache Hadoop is useful for data science. So I talked a little bit about schema on read, and I want to have the next slide will show a more specific example of how that reduces cycle times, why we data scientists really like that. I'm also going to talk about how Hadoop is really ideal for all the pre-processing, data cleaning, and all that kind of stuff that I talked about in the previous slide. Taking the raw data and creating the training set or the feature matrix for the model is very, very ideal. It's really ideal for that, especially if your raw data is very, very large. Again, generally, if you have a large enough feature matrix, if you have enough data and you can create a large enough training set, of course, larger training sets both in create better models. And then I'm going to talk a little bit about the large-scale parallel scoring. So let me start with this this example. So this is something that happened to me quite a bit, maybe 5 or 10 years ago, where Hadoop didn't exist. And what usually happens is I'm a data scientist. I have a certain model that already exists, and I have a new idea. Let's say I find that I can create 2 new features from sensor data. And so what you see on the top is the standard process that this works with, right? I think I need a new data. I go to my database administrator or somebody else in the operations team and say, hey, I need to put this new data in the database. I need to start collecting it so I can use it in my model. Well, that turns out to be a schema change project. What do I mean by that? Well, we, for a good reason, we protect our databases. Changing the schema is not something that we do lightly. There's usually a very rigorous process around this to make sure that we don't, harm anything else. And usually that takes, probably 6 months, although a lot of people tell me that I'm optimistic about that. So imagine that we go through that process and we change everything, and eventually, after 6 months, I start collecting the new data type that I'm interested in, and then I have to wait maybe 3 more months to get enough data of that type, and only then can I actually start my data science work, because, and hopefully I selected the right data. It was all a hypothesis that this will work. If not, I have to start the cycle again for 9 months. With Hadoop, one of the things that happens is the schema, there's no strict schema on write. So if I want to add more data, I just can open a folder and put it in HDFS. And 3 months later, I can start using the data right away. So the cycle time dramatically reduces that way, and I can experiment a lot faster. And this is why this accelerates data type innovation, because in kind of the current world, everything takes so long that not a lot of projects get done in a year, right? So you have that friction going on. So that's one thing that Hadoop is good at. The other thing that I mentioned earlier is it's very good for large-scale pre-processing, especially feature engineering and data cleaning. And the types of things we do there is we take the raw data, we transform it into a feature matrix. Through that, we do things like sampling. We do things like transformations, aggregations, normalization of data. Maybe it's dates or phone numbers or people's names or whatever. Sometimes people do things like entity recognition to figure out that 2 ways to write a certain name is the same person and normalize it that way. Of course, we do the regular structured data stuff like joins and merging different data sources. And sometimes we have, depending on the data, if it's textual data, for example, we might use natural language processing techniques. If it's a PDF, we might have OCR and then do some text recognition, text analytics on top of it. So there's a lot of different things that people are doing there. But a lot of the data, is the processing of this type of step is very parallelizable, and people use Hadoop to make that a fast and efficient process. So that's something we see quite a bit. The third point I want to say is that, of course, again, when we build a model, if we have more data, generally speaking, we can, larger data sets create better outcomes. And what you see here is a research that was done in 2001, almost like more than a decade ago. And this is two people done work in natural language processing. And as you can see, again, the more words and the more that we use in the model here, this is by Banco and Brill, the more accuracy we get, regardless of the algorithm that you choose. So generally speaking, that's the case. The reality of practical work is it depends on your data set and what you want to add. But generally, people talk about adding more examples, meaning more rows in your training set, or more features, maybe more predictive features. So a lot of times, what we see is with new data sets and new data types, features that were not possible before are added as new columns to the training set. And because of that, also, we sometimes need more examples to make the model more robust. So both of these things are happening. And that's another reason where Hadoop kind of enables larger data sets and better outcomes ultimately from the modeling exercise. All right, so the last thing I want to talk about is, so we trained our model, we pre-processed the data, we trained our model, now we want to deploy. We talked about it in the beginning. So once we have the model, one thing that we can do is we can export the model into this standard called PMML that was mentioned earlier. And that's essentially an XML description of the model. And once you do that, you can actually take your test set, which is the instances you want to use the model for, you want to score on, and you can use PMML to score at scale, right? So with Hadoop, what you can do is you can create your model, export it into PMML, and use things like Hive, UDFs to score across a lot of nodes in a cluster in parallel and to do it very efficiently. And with that, I'll transfer the presentation over to Michael.
Okay, thank you, Ofer. This was very, very insightful. You will see actually a couple of recurring topics you'll hear throughout my slides, one being the reduction on cycle time. But let me actually begin very briefly with a quick overview of PMML, the Predictive Model Markup Language industry standard, since some of you may not be fully familiar with that standard. It's really about reducing cost and complexity of operational deployment for predictive models across various different platforms. It's a very mature standard that has been developed by the data mining group, and it's really to avoid proprietary issues, incompatibilities across deployments, vendors, models, you name it. And with the ever-growing ecosystem of different data mining tools, different deployment platforms, Hadoop just being one of them, then this becomes ever more important. I mean, where would we be today without a SQL in the database world, without HTML in the browser world? So PMML, what is it? It's an XML-based language that basically defines your model as you've built it, and so you can move over that model into different platforms with one common standard representation. It's also supported by really most of the leading data mining tools, and that includes really all of the commercial major players like IBM SPSS, like SAS, SAP, as well as open source. So a lot of the open source tools like R, Python, and many others like KNIME really support the export of PMML, and that makes it portable across different vendors. It decouples you from being tied to one particular platform, one particular vendor. And really the mission behind that is to allow a clear separation of tasks, model development versus model deployment. The data scientists care about the best performance of the model. They need to look at different requirements than the IT world. Operational IT cares about uptime, latency, throughput, 24/7 availability and failover. So two different worlds that typically don't talk the same language, but if you can decouple that, PMML really becomes the bridge between both. And it eliminates the need for custom code. So you don't have proprietary code that defines your model moving into your operational environment every single time and the overhead associated with that. PMML in action is covering the complete workflow from input of your raw data to the decision that you take as the output of your model. And that can be as simple as a score or a probability, but it can be a business decision like approve, decline, high risk, low risk, whatever the business actually needs, what the following applications need in order to make the right next step in the business process work. It also includes pre-processing, which is sometimes not as well known as part of PMML. So you have raw data, you can derive value, you can have validation on your input, you can treat missing values, invalid values, missing outliers. And without having to write custom code around that or cleanse your data beforehand, your model knows what to do if that happens. If there's a missing value, score this value, this transaction, don't score it. Replace that missing value with a certain other value. So all of that can be done. Likewise, in post-processing, mapping it into bins and deriving other results from it. Now, the predictive model itself also can be of many different kinds. So it can be simple models like a regression, linear logistic models. It can be more complex ones like decision trees, support vector machines, advanced machine learning models like neural networks, or ensemble models that itself can contain hundreds of submodels that you can chain together, that you can have cascading events inside of that particular decision. So you can really extend that and cover all of your predictive modeling needs in one standard, and that's very, very effective. I'd like also to take one more step back here, actually, before we go into the actual application of that, which is, in big data, in the big data world, we always talk about the 3 V's. I'm sure you've heard volume, velocity, and variety as the 3 V's of big data. But really, what's more important than the first 3 is what I would call V number 4, business value. How do we actually take big data and derive business value? So on the slide, if you think about big data being kind of your source of potential value on the left-hand side, how do you move over to actually creating that, to do faster decisions and actions, gain faster insights? That's really I think the holy grail of big data and the application. And coming back to what Ofer mentioned earlier as cycle time, the faster I can move from left to right, the more value it will create for our business. And the key element in between the raw data and the business decision is really predictive analytics. The more data you have, the more you want to rely on statistical methods, machine learning algorithms. So predictive analytics suddenly becomes a mainstream application, a very important one. And with that, of course, having a common process and a common standard to deploy models becomes ever more important. Traditionally, this is what we see, and I think it resonates exactly with what Ofer just mentioned. Is, the traditional development cycle has the data scientist developing a great model, writing a requirements document in a Word format, probably 60 pages of describing what the model is supposed to do, and then IT goes off and re-implements that in Java, C++, in SQL, whatever it may be. So we'll have this big gap between developing the model and actually operationalizing it. So again, the end result is delayed insight on the business side, less accurate models because you still haven't been able to deploy the latest and greatest model, missed opportunity and loss of value. Really downstream, the impact is very, very measurable. For us, as on the technology side, it seems obvious that the simple solution is to make that crossover from development to operational deployment faster. And that's exactly what Zementis products do, and PMML as a standard was envisioned to really facilitate. So accelerating time to insight, time to deployment, reducing that model cycle time from literally 6, 9, or 12 months to days. Ideally, it would be minutes. You export your PMML from your data mining tool, you deploy it, and off you go. But in practice, we see usually a couple of days, a lag time here. But still, this is from several months to just a few days. So you can deploy your greatest models, your new models, much, much faster. You can deploy more models than you typically would do with a custom development and custom deployment coding process. So this really drives rapid time to value, rapid insight for the best models you could build. And if you think about hundreds and thousands of models that you'd like to deploy, this is really the way to go. Now on Hadoop, the key product that we have for that is called the Universal PMML plugin, or in short UPPI. And it runs, of course, natively on Hive on the Hortonworks platform. And what it does is it takes PMML and uses any of the tools on the left-hand side, commercial tools, open source tools like R, NIME, any of the predictive algorithms that you can think of, from very simple models. You may have 100 simple models, or you may have just 1 or 2 very, very complex ensemble models. Or you may have hundreds of thousands of ensemble models. This is actually high-end use cases that we see as well. You take that and move it with PMML on top of your Hadoop infrastructure. And that's really where you get the power of an established infrastructure that your IT team has put together. It's very simple to deploy it. It leverages basically PMML and Hive by turning PMML models into Hive QL UDF functions. So it becomes a user-defined function, and then you can seamlessly score that data on Hive. You get all the benefits of this infrastructure that you already put in place without any extra work. No custom coding, no extra work required, and your DBAs can run those scoring jobs on a regular basis, on a scheduled basis. You can transition over from just running one model on a small data set to running hundreds of models that you've built, or even thousands of models on very, very large data sets. So the scalability goes into multiple dimensions here. And so why do we prefer Hive? Why do we think Hive is a great platform? It has been one of the standard features of Hadoop, and it has a very vibrant ecosystem, and it continues to evolve very rapidly. That's why we think sticking with the baseline, the things that are in every Hadoop infrastructure, and making that better is a tremendous benefit to everyone who's leveraging Hadoop. So with Hive 13, you've probably heard about the Stinger initiative that really improved performance dramatically across all the aggregations, the joins, vectorizations, decoupling it from MapReduce. I mean, many opportunities to leverage faster performance by just upgrading to a later version. So you get that for free, that benefit. And there's even more to come with Stinger Next, which will really make it more interactive than it is today, so less batch oriented. All the things that we see from classical data warehouses. So if I take that, just contrasting UPPI running on Hive versus running it on an older version of Hive, really gives you performance improvement for free. You can scale simply by using a larger cluster. Of course, we all would expect that, but this is the slide, by the way, that just isolates performance improvement based on the UDF, so based on the pure scoring performance of your models. It doesn't take into account any of the other benefits that you get by faster Hive 13 performance. So simply scaling from 10 to 20 nodes takes the time and actually it cuts it in less than half. You get various benefits. You can optimize that. And likewise, if you have larger jobs and more models, going from 10 to 20 to 100 nodes will give you performance improvements without any changes to your model. So the key message is, again, don't touch your models. Once you've developed that, that's your key asset. Scaling your infrastructure will get you the additional benefits. And with Hive 13, you get an additional boost for free if you just enable TES and ORC, the columnar storage capabilities. And just enabling those features, which is 2 commands, enable TES, enable ORC, you get almost 30% performance. Again, only on UDF scoring, not even taking into account faster query performance on all other aspects. So leveraging one standard element, Hive, in the Hadoop stack for the scoring gets you all of these benefits. But I think we've looked at many slides already, so why don't we take a quick detour and actually look at a demo of UPPI on Hive running on the Hortonworks sandbox, and just demonstrate how simple it is. 2 steps. Take your sample models, create Hive UDFs, and run. One of the examples we're going to look at is a customer churn model today. Again, this runs on a very small cluster. And with that, Jackie, can you actually hand over the controls to Marlon to run the demo? Okay, perfect. So again, this runs on the standard Hortonworks sandbox that you can download it on a simple laptop. Latest HTTP distribution, of course, with Hive. Our product, the Universal PMML plugin you see here, is already installed. And let's just take a look at the PMML examples that we actually ship with our product. This is something that allows you to get started very quickly. We actually have about, I think, 22 models here, and they're just grouped in different directories here with by different model types. So you see clustering models, mining models, neural networks, tree models. So a wide variety of different models. And why don't we take a tighter look here at the neural network types? There you see exactly what we ship, particular with those examples, and you see there's not much magic to it. You have the .pmml models files, so this is the XML that contains actually the models itself, and then you have CSV, so some test data to actually run this. Later on we'll take a look here at this customer churn neural network model for and then execute that, so you see how simple that is. But let's start actually with taking all these 22 models and converting them into PMML. And all you need to do is run a simple script called prepare PMML, which takes as an input the folder that you give it, and that folder and its subfolders contains a number of files. So here in our case, it's our 22 different models, and it will take those models and generate basically UDFs out of them. So it will convert, it will validate those models. It will give you some warnings, or it could actually produce you some error messages if something's wrong with those files. So it's very verbose here, as you can tell. And keep in mind, these are 22 different models, different algorithms that come from different modeling tools that we just converted into UDFs. That's how simple actually the process is. And there's no difference if you have 1,000 models. You just run this script, and it basically creates a deployment package for each of your models. So as a next step, all we need to run is a query. So let's do that with our customer churn example. And here you see we're typing in the query example, which of course will take a little bit to start up on our little sandbox here, but it will just take the jars that we created with PMML preparation. We'll create the UDFs out of that, and then kick off and fire the query. And then the query you will see in a second here on the screen. It will create the MapReduce job, and then start the MapReduce job, and give you all the information as it goes through that, and eventually it will produce an output. The example that we're seeing here is a customer churn model. So this is a neural network model type that was developed in R. We're just scoring about 10,000 records, of course, for the demo purposes today. It's an example out of the telecom world, so it is looking at customer churn. If I'm a customer of one wireless carrier and I have a high risk to churn, maybe the wireless carrier would like to do something about that before it happens. So these are actually very complex models that take complex inputs from spending patterns, the items that you purchase, the support tickets you may have had. But this particular model also takes into account some social media data. How many friends do you have that are with the same carrier? What's their spending patterns and their risk to churn, and kind of takes that social media influencer role into account. And whenever there's social media in the mix, you know that you can generate many transactions and a lot of data. And so Hadoop is, of course, an ideal use case here. And as you see here, the output for this particular script, we just scored the 10,000 rows. Here is the customer ID, and then it's producing a likelihood, a probability to churn for each customer. Interesting, and to keep in mind here is, this is the super simple demo. These two steps is all that is required to run basically any kind of number of models or complex models. So the same two steps apply if you want to run one model or 1,000 models, if you run it on a terabyte or just 10,000 rows, or if you run it on a single node sandbox, or if you want to run this on a 100 or 1,000 node cluster. No difference. Again, operational efficiency is what we're trying to achieve. Jackie, can you switch back to my presentation, please? Thank you, Marlon, for that wonderful quick demo. Let me do that. So really keep in mind, this demo it was a real model, a real example, and it's no different for any of your models if you have many or one, to deploy that super efficiently. And the inherent scalability that we get here goes into multiple dimensions, number of models, or even think about model complexity. If you were able to run only linear models so far, now you can actually do the same thing with complex random forest models or other ensemble models that would be computational prohibitive otherwise. Now you don't have to worry about the data size because all you need to do is scale your Hadoop cluster. If you, instead of running this in a day, you want to run it in an hour. It's just a matter of scaling up your cluster size. So with that, the presentation is actually coming to an end. I just wanted to summarize that what we see here is a fundamental shift in capabilities to deploy predictive models faster. And this is applicable across all industry verticals, thinking of Hadoop as a platform, PMML as a common process and standard, and the Zementis Universal PMML plugin as the enabler to ramp those models onto your Hadoop cluster. We've seen this with our products, accelerates deployment across the financial industry for fraud and risk scoring, for example. Think about Internet of Things, sensor data, lots and lots of data that you're collecting here. Again, it doesn't matter what type of data it is, people data or machine data. The application of the process is always the same. So, for a data scientist, the downstream effort doesn't change. Marketing, similar to what we looked at, churn reduction. Of course, you have upsell, cross-sell opportunities and marketing optimization. So broad applicability, and that's why we emphasize, a common platform, a common process, and a common standard will really enable efficiencies to take advantage and generate value from big data. And with that, Mark, I'll hand over the moderation back to you.
Great. Before people leave, before we start the Q&A, I do want to remind everyone to please keep an eye out for an email we're going to send a couple hours after this webinar. It's going to contain a link to a download of a white paper on ARN Hadoop by a very well-known big data analyst named James Taylor. So I hope you'll keep an eye out for that. I did want to thank both Mike and Ofer for their extremely informative presentations. And I have a number of questions here from the audience. There are a couple of questions that I am going to actually answer first. One is a question, I believe Mike mentioned this. What does UPPI stand for? That stands for the Universal PMML Plugin. And a similar question is just a point of information. Mike had shown a slide that showed typically what we find is 6 months to deploy a complex predictive model, and we're shortening that down to 2 days. And there was a little bit of a question about where those stats come from. That's our experience at Zementis. And the only reason it takes 2 days to deploy is actually if you're using us, it deploys immediately, but that model will often still need to go through a compliance check around regulatory issues, around security issues, and around privacy issues. So that's where that comes from. I've also gotten a couple of questions around, will the slides be available for download? They will. We'll figure out if we'll do that via SlideShare or another way, and we will we'll inform you of that via email again. So I'm going to ask you to keep an eye out for our communications and open them. With that, let me ask Ofer to talk a little bit. We got a couple of questions around Lambda architecture and Hadoop, coming from a couple of different angles. So whatever you'd like to say about that would be very informative to the audience, I think, Ofer.
Sure, happy to. So Lambda architecture is essentially the idea that we combine both batch and streaming in a single process. And the reason you want to do that is because sometimes some of the data comes in more real-time fashion, and you kind of want to, so a lot of times you build a model in batch and you retrain it, let's say, once a week or once a month or even once a day, but you got more recent data and you kind of want to incorporate it into your architecture. So we see that use case coming up more and more, say in the last, maybe 6 months or a year. And as part of the Hortonworks data platform, we have, of course, Storm, which is the main component that's typically used for the streaming part. And with Yarn, you can combine Yarn and Storm together and into an architecture that supports the Lambda kind of intent. So I would say I would add to that in terms of the data science component, I mean, you can do a Lambda architecture for ingest and you can do it for ETL. And in data science specifically, again, sometimes you would want to have a model that has these two components. Previously in my life, I was at Yahoo, and I think we also implemented something similar to that there, where we had click-through rate prediction on search advertising, and you would have a regular model, but then you have some queries that came in that were very, very fast and coming very fast, and updating. The marketplace would update very fast, and the changes will be dramatic. So we wanted to update the models for those keyword marketplaces that were very fast changing. So that's what I have to say. If there's other questions about that, please send them to Mark so I can respond further.
There's actually one particular question here more related to the Universal PMML plugin, UPPI, if it also runs on other versions of Hive or only on 13. It actually does. So it's not coupled to Hive 13. It goes back 12, 11, 10. So Hive, of course, 13 gives you an extra performance boost. And then there's an additional question here, I think, about is there a limit to, let me see, is there a limit to PMML model complexity or the number of models? And that's a simple answer is not really. So there's not a practical limit. It's actually quite the opposite. So the more complex the models are, the higher the benefit it really is for using PMML on the deployment on a common standard. And likewise, the complexity and the number of models, the more it increases, the more effective your scoring offload will be on a massively parallel Hadoop cluster.
Another question that we got was for Ofer around What do you see when you go into an organization? What enables? What are the enabling factors that make a Hadoop project a success culturally? What should people be keeping an eye out for around those kinds of issues?
Yeah, thank you for that question. So I think it starts actually from, and I kind of hinted at that in my presentation too, that there's some kind of a magical thing that happens when you put all the data in one place. And I've also seen it at Yahoo when we started using Hadoop in 2007 or 8. It's just, it's a new thing, and you sort of start ingesting all these data sources, and all of a sudden, the friction of using the data and having access to the data goes away. And so I think it's very important to, first of all, have an initiative to ingest as many data sources as possible, of course the useful data sources, into Hadoop, right? So you set the cluster up, you make enough space. Again, the cost of this is significantly lower than anything else. So we always think of the cost of more storage as very negligible. But what happens is then the data scientists in the organization all of a sudden discover, hey, I got this cluster, and in order to run some analysis or some hypothesis or build some predictive model, all I need to do is to get access. I need an account on the cluster, and that's it. As opposed to if I need to do it otherwise, I need to buy a bunch of machines. I need to get budget for that. I need to get people to put the data over there. I mean, so before I actually can do anything, I need to do a lot of work, get a lot of friction, get a lot of approvals. So if you invest in sort of putting together this data lake, I think that creates a lot of opportunity. And then sort of things evolve from there pretty much on their own. You'll see a lot of data scientists across the organization getting really interested in this and understanding that all of a sudden they can be a lot more effective, a lot faster. And so that's one of the key things that happens. In addition to that, just, Hadoop is a new technology, and so I think it's very important to have people train on this technology. So there's a lot of training classes you can have. We provide a lot of training classes around this, and really support your team that are doing the Hadoop project to kind of educate themselves, to be expert on this, both if they're developers on Hadoop, if they're admins on Hadoop, if they're data scientists. The benefits are large, and there's a lot of benefits to be had, but it is new, and you got to support the team and give them the right path to success. So support the team is the second one, I would say.
Great. And Mike, I know one of the common questions that we get is, great, I've got all this data that I'm putting into Hadoop, and I want to score against it, but because of the way I've put it into Hadoop, it might not be quite ready for scoring. It's a little messy, it's a little dirty. What kind of capabilities does PMML have to massage that data before I score it?
Mm-hmm. Great question. Actually, always operating on the raw data is one option. So PMML actually has lots of pre and post processing capabilities. So you can derive values. So you can do quite a bit of pre-processing of all sorts and shapes and forms. And that's very critical if you want your model to move over. In Hadoop, you of course have also the capability in let's say Hive to use the HiveQL language to do some filtering, joining, aggregations on the fly. So it really depends on the individual use case. If you're leaning towards more doing that in the Hive world, in the SQL-ish kind of approach, or if you combine a lot of that pre and post processing into your models. It's really on a case-by-case basis what's easier, where the skills are, and also what changes more frequently. So if you always know this is my raw data, then maybe having it in the model is actually a very, very elegant way to save that.
And great. And the next question is for Ofer, going back to a little Hadoop history here. Back when you were at Yahoo and Hadoop was just, beginning, and the decision was made to make it open source, did you and the team, 10 years later, ever think it would have, I mean, was it at the time, oh, this thing's going to get the kind of traction that it has? Or do you look around today and go, wow, what just happened?
I think it's the wow, actually. I mean, it was very early on. It was very exciting, but we were busy kind of implementing our business case on it. And but if you see the growth that Yahoo had and the success that Yahoo has seen over the years in deploying Hadoop on all these different use cases, if you take a bigger view from above, it's pretty amazing. I mean, they have a huge installation with a lot of businesses relying day in and day out on the Hadoop right now. But definitely, I don't think for one at least, did not really expect it back in the early days. You know, maybe I would say in 2009, 2010, I could see that coming, but not earlier than that.
Great. Well, listen, we always want to be very careful with people's time and show our respect for that. Our hour is essentially up. So once again, I want to thank everyone for attending this webinar. One of the common things I like to say when I'm saying farewell is I'll see you around the sandbox, and in this case, I'll see you around the Hortonworks sandbox. That's where all the cool kids are these days. Talk to you soon, and be well.